signal or a continuous signal, and if it is going to be discrete in the time domain, we call it as a discrete signal, and if it is discrete in the amplitude also, we call that as a digital signal. So in this course, we are going to study only about the analog communication. Now the analog signals only will process it and see how exactly we are going to get back the original signal that we are going to have it. So we are going to have all the communication signals, a continuous signal that we are going to have it for the time being. In your digital communication and advanced courses, you will be going for the other types of communication also. So in this course, we are going to study about the communication of a continuous signal. Therefore, we are calling this course as analog communication course. That's what we are going to discuss further in this course that we are going to have it. So we are having a source and a destination, and in between we are having a wired or wireless system that we are going to have it. So to transmit this, we require certain modifications. That's what we said, what you call the modulation that we are going to do for the signal that we are going to have it. The audio signal is going to convert it to a signal by this mic, and then this electrical signal is going to be modified or modulated to be transmitted. At the receiving end, this modulated signal is going to be received along with some other signals, and will rectify those signals, process it, and demodulate it or detect the signal, so that we can get back the electrical signal. From that you get your audio signal and put it onto your microphone, so that you can hear your audio signal, or put onto a recorder if you want to hear it at a later time or see at a later time. So this is what we are going to have it in your communication between your source and destination that we are going to have it. So why you require a modulation, or what is need for modulation that we are going to have it, so that we can see what are the variations that are possible in this communication system that we are going to have it. So we have only mic signal. This has been put on the entire channel. Only one signal is transmitted. So as we say that this is a audio signal, it is of some 30 Hz to 20 kilohertz, the signal that we are going to have it, a maximum bandwidth of 20 kilohertz. And even this maximum bandwidth we are not going to transmit, because the maximum power or the energy that we are going to have it is within the 30 to 3 kilohertz or 4 kilohertz that we are going to have it. So the main signal 4 kilohertz to 20 kilohertz, you are going to have only either 2 to 5% of the signal, therefore will not transmit this. So if you put one voice signal, the entire channel, without transmitting any other channel or any other signal that we are going to have it, then it will be waste of the capacity of the channel that we are going to have it, because channel is a wide open depending on the capacity of the transmission system that we are going to have it. On this entire bandwidth, you are putting only a 4 kilohertz signal that we are going to have it, which will be a waste, like a single passenger in the entire bus or the entire train. No necessity for a single passenger to have for the entire transport system. Whereas in a bus you may be having 40 to 60 people, and in a train you may be having hundreds of people. So that means you can transmit number of people on the train, but whereas you are putting only one. So you have to keep the number of signals to be increased onto the channel. So how to keep these things on the channel without any interference between the different signals that we are going to have it. So we want to utilize this modulation, or what we call frequency translation, to see that number of signals are going to be put onto the channel and able to receive at the receiving end effectively. Not only that one, as we are seeing that we have this audio signal. There are about 60 students here. If I put a question, all the 60 people are going to answer at a time. What will happen? No signal will be heard. None of you are able to receive the signal because your ear is going to be able to receive one signal at a time. And all these signals are in the same band of 32, 4 kilohertz or 20 kilohertz, that way are going to have it. So once they are all on the same band, all will be mixed up and you will not be able to hear any signal, that way are going to have it. Therefore, to avoid these things, we require what you call modulation. So what is the necessity for modulation, or what are the advantages of going for a frequency translation? So we are going to shift the frequencies from the required baseband signal to some other frequencies so that you can effectively communicate number of signals on the same channel without any much interference, that we are going to have it. We'll see that interference and other things, and they are talking about noise and other things. But for the time being, we say that we are using this modulation to effectively communicate without any interference. What is the need for modulation, that we are going to have it? So we require what we call frequency multiplexing. As I said, we are going to transmit number of signals on the same channel. Let us say that we have n number of signals of the same frequency band. This signal is having the same 30 Hz to 4 kHz signal. This, if you translate to different bands by using what you call the frequency multiplexing, you can transmit all these signals, n signals, simultaneously without affecting other signals, and then receiving at the receiving end by using different filters, the band pass filters, that we are going to have it. So let us say that you have the signals M1 of t, M2 of t, Mn of t. N signals we are going to have it. Then let us say that we have different carrier signals with the carrier frequencies of omega C1, C2, C3 and Cn, that we are going to have it. So these signals, which are at the baseband signal, and using this we call it as the baseband signal, and this is a carrier signal which carries the baseband signal, that we are going to have it. And the initial baseband signal may be having a frequency spectrum like this. This has to be put up with all these frequencies. This is one signal, and this is another signal, this is another signal, and so on. N signals we are going to have it, and all the signals are shifted in the frequency and then combined without any interference. At the receiving end, if you want this M3, you have a band pass filter. You can eliminate all the signals and get only this, and do the pre-processing, and then process the signal to get back your signal M3 of t, that we are going to have it. So that's what we are going to have it in this frequency multiplexing, that we are going to have it, combining the signals by using what you call frequency translation. This baseband signal from 0 to FM is transmitted between FC3 to FC3 plus FM and FC3 minus FM. So this will be the signal that we are going to have it. Translated signal that we are going to have it in what you call multiplexing. So that is one need. You can effectively put number of signals on the same channel. The second requirement that we are going to have it is effective. When we are transmitting this using an antenna system that we are going to have it, a communication channel, by an antenna to radiate space. To radiate the signal, this antenna is going to have a certain size. Going to have it. So what should be? So this size of the antenna should be half of the wavelength that we are going to have it. So to effectively signal that we are going to have it. Let's say that we have the signal 3 kilohertz. Your voice signal, we are saying that effectively that 3 kilohertz is the main frequency that we are going to have it. So what should be the radiator size that we are going to have it, or the antenna size that we are going to have? Pardon? So this lambda equal to C by F, where C is the speed of light, because this is an electromagnetic signal putting onto the space and considering that it is a vacuum. Anyhow, if we have A, then that we are going to have it, but normal calculation will see that this is the speed of light, C by F. Therefore, this will be equal to 3 into 10 to the power of 8 by 3 into 10 to the power of 3, which will be about 100 kilometers. Three into 10 to the power of 8 by so kilometers is the is it possible physically? Not. You can't straight away put this signal. Suppose if you say that this is going to 1 megahertz. That means so if you further increase the frequency into gigahertz range, the size of the antenna. So your antenna size is going to be one of the parameter to frequency. So you have to transfer from a high frequency signal. Radiate the base having high frequency. So what we mean by need of the modulation radiation that we are going to have it. The other one is narrow. What do you mean by narrow banding? Narrow banding. Narrow banding. Decreasing. Say that this is 30 hertz to 4 kilohertz. So narrow banding. Mean by that, so your signal is going to be So if we have if you say that you have designed your antenna 3 kilohertz, signal 30 hertz. We are not able to going to have it because so therefore you can't straight away put this if you are translated the signal having a carrier of 1000 frequency. So that means the ratio will be 1:003 because 1000 kilohertz and 1000. This is 1:1.003. So your same antenna is now actually radiating both ends, but your baseband signal is 30 hertz to 3 kilohertz. This we are not reduced anywhere. What we have to put into a higher plane, so the ratio between the minimum and maximum are now become 1:1.003, whereas previously we have 1:100. The same signal 30 hertz to 3 kilohertz is there. We are not reduced any frequency requirements for the baseband signal, but by using this carrier, we have effectively reduced the ratio between the minimum and maximum frequencies of the signal. That means now with 1000 kilohertz signal, the band is going to be very, very narrow because this is 1:1.003 only. That means both ends you can effectively radiate the same size of the antenna that we are going to have it. That's what we mean by narrow banding, that we are going to have it. Other point that we are going to have it is common processing. Why you require a common processing? We have a number of transmitters. The baseband signal is going to be there. Number of transmitters are there. Suppose you have one station at Vijayawada, one station at Hyderabad, another station at Visakhapatnam. 3 stations, let us say for example. All the 3 are transmitting same audio frequency, baseband signal, modulated by different carrier signals, depending on the carrier frequency of the station. So your baseband signal, carrier signal will be from 535 to 1640 kilohertz, the medium wave band that we are going to have it for your Hyderabad, Visakhapatnam or Vijayawada that we are going to have it. Different band frequencies are allocated for these stations in this range, but all are having the same baseband signal, audio signal. So they are going to modulate with their carrier frequencies F1, F2, F3, and all have been transmitted. So for some time you want to receive Vijayawada station, and sometimes you want to receive Visakhapatnam station, because that's program you are interested, right? Therefore, the frequencies are now different for Vijayawada and Visakhapatnam. You can't go on having different receivers or different radios for you to receive the signal. Or you have Gemini TV, ETV, ETV News, and so on. You have only one receiver. What you are doing? You are tuning to a particular station or a particular channel and process it, the signal, in the same way for any signal that we are going to have it, by keeping what you call intermediate frequency from the baseband, the carrier frequency of the different channels or the stations. You convert all these signals into a fixed intermediate frequency signal. Then you process it to eliminate the noise, to increase the amplitude, get the required amplitude, then demodulate it by using our different demodulation techniques that we are going to have it. So instead of having different processors for different channels or different stations, to have a common processing, we want to have a modulation that we are going to have, so that all these things are going to be kept into different frequency bands by using a center frequency of what you call the intermediate frequency that we are going to have it, along with your carrier frequency. So all those carrier frequencies are going to be brought down to an intermediate frequency. Then you have the processing. Anyhow, we see that how we are going to getting down the intermediate frequency when we are discussing about our radio receivers, the last chapter that we are going to have it. Okay, so these are all the requirements for the modulation purpose, or the need for modulation is going to be basically these 4 points are required, so that we will be having an effective communication between a source and destination by effectively using the channel also. The channel also has to be effectively utilized. So for that, we require all these requirements of this need for modulation that we are going to have: multiplexing, the radiation that we are going to have it, narrow banding, and common processing that we are going to have it. So these are the things that we are going to have it. So once we have these things, what is that we require for further processing that we are going to have it? So after this frequency translation, what we said this need for modulation is the frequency multiplexing that we use. So what is this multiplexing that we are going to do it? Is it only frequency you are going to multiplex, or as you have put this, time also? So you can multiplex the frequency signal or the time signal that we are going to have it. The frequency signal, as we said, that number of signals we are going to keep it at the different frequencies of the carrier. So you have n channel signals, and all the signals are multiplexed by using different carriers. You have a modulator 1, which will be having required baseband signal along with the carrier frequency FC1. Another modulator with a carrier frequency of FC2. With what are the signals that we are going to have? One student, another student, and third student, fourth student, so on. Different signals are there. And all these signals we are multiplexing with, or modulating with different carrier frequencies, FC1, FC2, FC3, so that these FC1, FC2, FC3 are chosen such that there will not be overlapping of these signals that we are going to have it, and receiving end by using different band pass filters, you can get back the signals that we are going to. That's what we are saying, that tuning your channel, ETV channel or Gemini channel or anything, you are having a band pass filter there by putting that. So that means we are selecting only particular radio station or the channel that we are going to have. So this is what your frequency division multiplexing. So we have n number of input signals, and we have n number of modulators. You have n baseband signals and n modulators, and each modulator is having different carrier frequencies, and these carrier frequencies are chosen such that they will not be overlapping after modulating the signal. That means all these signals are put onto the same channel and they combine or multiplex and then given to the same radiator, the antenna system that we are going to have it. Then at receiving end, you have a receiving antenna and the radiator, receive it, and this will be receiver now. So at this input point, you have a band pass filter to choose which station you want or which signal you want. Select that, then have a common processing, then have a demodulation, then have a display or the recording system that we are going to have it. So this is what we are going to have it in our frequency division multiplexing that we are going to have it. That's what we said. Two methods of multiplexing. Now we are going to have it. Anyhow, in the advanced courses, you are going to have different multiple systems with multiple access systems and so on. So for the time being, we'll limit to our frequency division multiplexing and time division multiplexing. So you know what is meant by frequency division multiplexing, how frequency division multiplexing is going to be achieved. So you are going to have n signals, n modulators, n carriers. Combine that, add up, and then translate it, transmit the signal. At the receiving end, you do the reverse process, right? You are going to get back the original signals appropriately without any interference that we are going to have it. Then what is this time division multiplexing? You have seen the sampling, right? So given the signal, how to sample the signal so that at the receiving end you will be able to get back the original signal without any error. Pardon? Sampling of the signal. You have written the examination also. Huh? FS? Greater than 2 FM. The sampling frequency of the signal should be greater than twice that of the maximum frequency of the band limited signal that we are going to have it. 2 FM. Or we are sampling at the Nyquist rate, minimum rate that we are going to have it, or more than that. So 2 FM is minimum, and greater than 2 FM, you have the rate to be more. So you have the signal sampling at different rates that we are going to have it. Let us say that you have the signal something like this. You have the sample signal here and another signal sample here. This is first sample and this is the second sample and third sample and so on. And as I said again, we are not going to transmit only single signal. In between these two samples, there is a time gap between first sample and second sample. So this time gap, we want to utilize it to transmit more number of signals that we are going to have it. So you may keep this is for signal 1, this is for signal 1. So have a signal like this. Okay, this is for 1 and this is also for 1. So have another signal. This is for 2. This is for 2. And then this is for 3. This is for 3. And this will be for nth signal. So similarly, you may be having a signal n here. Then you are going to have another signal which corresponds to 1. So you are going to have n number of signals sampled and then multiplexed in the time domain. So between sample 1 and 1 of the same signal, you have multiplexed n samples here. And the receiving end, you are going to synchronize and then select only that particular signal that we are going to have it. So that you can pass this to again to a low pass filter after selecting all that samples of first signal. Pass to a low pass filter, you are going to get back your original signal. To get your second signal, sample only those samples of the second signal. Then pass to a low pass filter, you are going to get back your second signal and so on. So what we are doing is, you have n signals, 1 to n. You have n samplers at the required sampling rate. Because all signals are the same frequency, you have the same sampling rate. Then sample them and then combine them by doing what you call a commutator. Sampler S1, S2, S3, Sn. So all these things are going to be combined into what you call a commutator. You have these n signals and all these n signals are sampled at the sampling rate. Then these signals are going to be put into the commutator so that all these signals will combine in the timing diagram what you have done previously. Then this will be the channel that we are going to have it. At the receiving end, an opposite way of a decommutator is going to be there, which is in synchronization with this commutator. So when this is at 1, this will be at 1, and this is at 2, this will be at 3, and so on. So that a synchronization between is maintained between your transmitter and the receiver that we are going to have it. Then we are going to select only this channel is going to be only for the samples of the signal 1. Then have a filter, and you are going to get your M1 signal that we are going to have it. All these signals you can get back the original signals by passing through required filters that we are going to have it. So this is about your TDM process that we are going to have it, a time division multiplexing of the signal. So you can have a time division multiplexing or a frequency division multiplexing that we are going to have it to multiplex number of signals that we are going to have. Okay, so that is what we are going to have, and this will be having, and we are discussing about our pulse modulation techniques of PDM, PPM, and so on that we are going to have. Okay. What is this frequency translation? The process of frequency translation that we are going to have it. So your basic requirement for transmitting a number of signals is your frequency translation or the modulation process that we are going to have it. So we call it as frequency translation or what we call modulation. In the modulation, what we are doing is we are having the baseband signal at a particular bandwidth that we are raising to a center carrier frequency FC that we are going to have it. So in this frequency translation, what we are doing is, let us say that Vm of t equal to some Am cos omega m of t, right? You have your baseband signal, which you are considering as a sinusoidal signal for the time being, a single frequency signal with the frequency of, what is the frequency of the signal? The radial frequency is omega m. This omega m is nothing but 2 pi fm that we are going to have it. So this you can write it as Am by 2 of, using Euler's theorem, 2 exponential signals, right? This will be equal to Am by 2 e power j omega m of t plus e power minus j omega m of t, or 2 by fm of t, because your frequency is there. So what is the frequency domain representation of the signal? Frequency domain representation of the signal. This is a sinusoidal signal. What is the frequency domain representation of the signal? You have studied in the signals. The spectrum of this. What is? What is the transform of this? What is the signal? Pi. Where is pi? Two spectral lines, one at Fm and another one at minus Fm. That's what we have, e power j omega mt and e power minus j omega mt. Okay? So you have two spectral lines corresponding to this sinusoidal signal Am cos omega mt with the magnitude of Am by 2 and at Fm and minus Fm. This is your baseband signal. Right? So let us say that we have your carrier signal Vc of t equal to some Ac cos omega ct, and this omega c is much higher compared to your omega m that we are going to have it. As I said, 3 kilohertz and 100 kilohertz or 1000 kilohertz, right? With much higher frequency that we are going to have it. So this will be having a spectrum at minus fc. So this will be having again two spectral lines as the spectrum, because this is again Ac by 2 e power j omega ct plus e power minus j omega ct, right? So you have again two spectral lines as the spectrum of your carrier signal. Now what we are going to do is you multiply the signal S of t equal to Vm of t into Vc of t, which will be equal to Am Ac cos omega ct into cos omega m of t. The product we are taking Vm of t into Vc of t. That's what we are taking as the output of your frequency translator or modulator. So output is Am Ac cos omega ct into cos omega mt. So this is cos A into cos B. So what is the output of this? Into a summation cos of omega c plus omega mt plus cos of omega c minus omega m of t by 2. Okay? Therefore, what we are going to have it is Am Ac by 2 into two sinusoidal frequencies, one at omega c plus omega m and another one is at omega c minus omega m. each sinusoidal frequency will be having two spectral lines. Suppose if you say that cos omega c plus omega m, that means you are going to have the spectral line at fc plus fm and minus of fc plus fm, that is minus fc minus fm. Two spectral lines you are going to have it. And similarly for omega c minus omega m, you are going to have another two spectral lines. One at fc minus fm and another one is minus fc plus fm, that way are going to have it. Therefore, you are going to have the spectral lines this is fc plus fm, this is fc minus fm, center frequency as fc. This is minus fc minus fm and this is minus fc and this is minus fc minus fm. This will be the spectrum. Four spectral lines that we are going to have it. fc plus fm and fc minus fm. And this is minus fc minus fm and this is minus fc plus fm, that way are going to have it. So you have the baseband signal, the two spectral lines fm, whereas now you have four spectral lines, that way are going to have it. The baseband signal is having two spectral lines, whereas the moderate signal or frequency translated signal is having four spectral lines, that way are going to have it. So here your baseband signal cos omega mt is having only single frequency or what you call single tone. That's why we call it as single tone modulation or single tone frequency translation, that we are going to have it. A carrier is there cos omega ct and that is modulated by your baseband signal or single tone signal cos omega m of t, that we are going to have it, which is going to give you four spectral lines. Instead of a single frequency in the baseband signal, let us say that we have omega m1t, omega m2t and omega m3t. Three signals are there, or three frequencies are there in your baseband signal. That is omega m1 of t plus am2 cos omega m2 of t plus am3 cos omega m3 of t. These frequency components are there, omega m1, omega m2 and omega m3. What will be the spectrum of this signal? So this cos omega m1 of t will be having two spectrums, fm1 and minus fm1. Similarly, this will be having fm2 and minus fm2, and this will be having at fm3 and minus fm3. Let us say that fm3 is larger than fm2 and fm2 is larger than fm1. Then your spectral line will be three and three, six spectral lines. You are going to get it because each frequency component of omega m1 gives you two spectral lines. Therefore, how many are going to have it? Six spectral lines you are having. When you have three tones, your baseband signal, that we are going to have it. Okay? This signal you are multiplying with the same cos omega ct. The carrier is the same because you have only the baseband signal having three frequency components now. That means whatever I am generating now three frequency components instead of a single tone frequency. So this entire signal is multiplied with cos omega ct. What will happen? AM1 AC cos omega CT into cos omega M1T plus AC AM2 cos omega CT into cos omega M2T plus AM3 AC cos omega CT into cos omega 3T. So three products are there, right? Like this. Omega M1, omega M2, omega M3. Three products are there. So each of these product is giving you 4 spectral components. And you have 3 such products. So how many spectral components you are going to get? 12 spectral lines you are going to get. And how many spectral lines are there in your baseband signal? 6. When you have 6, you are getting 12 spectral lines. When you have 2, you have 4 at the output. When you have 6, you have 12 spectral components. That is double the number of baseband signal frequencies you are having in your spectral domain of your output signal that we are going to have. The frequency translated signal is going to have double the number of spectral lines that we are going to have it. So if you have 4 tones, you will be having 8 spectral lines in your baseband signal, whereas 16 spectral lines in your output of the frequency translated signal that we are going to have it. Now instead of that, let us say that we have your Y signal. As we are saying that this audio signal is going to be having a frequency of 30 Hz to 3 kHz or 4 kHz, let us say. So that means all frequency components are available in this voice frequency, 30 Hz to 4 kHz. So what will be the spectrum of your voice signal? A general M of T will be having a spectrum like this, 0 to FM. Zero to FM. All frequency components are there. That is up to 4 kHz, let us say. So this is the spectrum of a generalized signal having DC signal, and all the frequency components also are there. This you are multiplying with a carrier, same carrier, cos omega CT. Then what will happen? M of T into cos omega CT is the output. M of T into cos omega CT. Right? M of T is having a spectrum like this, which I am representing as M of F. Okay? The spectrum of your baseband signal is going to be M of F. So that signal we are multiplying by cos omega CT. So what should be the output spectrum domain? What should be the output of the signal spectral representation of M of T into cos omega CT? M of T into cos omega CT. Go back to your signal scores. Okay, because here we are saying M of F, this is M of F plus FC and M of F minus FC. Two frequency domain spectral lines you are going to have it. Therefore, your spectral representation of the output will be like this: M of F plus FC and F minus FC, that we are going to have it. This is what we have done as the modulation principle of your Fourier transform property. M of T into cos omega CT. Here we have said F of T into cos omega CT. So F of omega minus omega C and F of omega minus omega plus omega C. So the same thing you are going to have it here. So when you have this 0 to FM, So you have maximum frequency of FM. So what is the bandwidth of the signal? What is the bandwidth of your baseband signal? Bandwidth of your baseband signal. 2 FM. How many of you say 2 FM? 1, 2. Where is 2 FM? What are the frequency components? 0, 2 FM only. There is only negative frequency, you are going to have it. E power j omega ct and e power minus j omega ct. There are no frequency components. FC is the same, FM. So the baseband signal is having a maximum frequency component FM. So the bandwidth of your baseband signal is only FM. But whereas, what is the maximum frequency of the transfer signal? This is FC plus FM and this is FC minus FM. Whereas this is minus FC plus FM and this is minus FC minus FM. This is negative part of this. So what is the bandwidth now? FC minus FM to FC plus FM. That means frequency translated bandwidth is now 2 FM. Your baseband signal bandwidth is FM and frequency translated or modulated frequency bandwidth is now 2 FM. The same convention that 2 spectral lines, you have 4 spectral lines twice. Now we have 0 to FM, a continuous spectrum, so that is double to give you 2 FM as the bandwidth that we are going to have it. So as you increase number of frequency lines in your spectrum, the number of frequency lines are doubled in the frequency translated signal, because this is linear. As number of frequency components increases in the baseband signal, the similar way the number of frequency components are doubled in the frequency translated signal. If you have 2 frequency bands, frequency lines in your baseband signal, you have 4 spectral lines. If you have 6, you have 12. If you have 0 to FM continuous, you have twice that of that one that we are going to have, 2 FM. Therefore, it's a linear multiplication of 2 that we are going to have. Therefore, this analog modulation, that whatever frequency translation that we are going to talk about, we call it as a linear modulation, a linear translation that we are going to have it. Okay, so this is what your frequency translation to have your shift from baseband signal to a higher carrier frequency of FC that we are going to have, so that you can have all the channels or all the signals to be transmitted in the same channel by doing what you call frequency division multiplexing that we are going to have. Okay, so this is what your frequency translation, and then go through the steps, all the steps that we are going to have it, so that you can explain how exactly our spectral lines are coming in and what modifications we are going to have it. So we are talking this frequency translation and we are saying what is called modulation. What do you generally mean by modulation? Modulation. Adding carrier. Okay. One is adding carrier. Any other? Modulation. Modulation. Low frequency with high frequency. Any other? Suppose if you go on speaking with the same tone, what do you say? Without any variation, without any modulation, we are saying that the signal is coming in. Suppose if I raise my voice or reduce my voice, depending on the stress that we want to give on the point that we are going to have it, there is a variation in the level of the signal that we are going to have. Basically, your modulation means changing the level of the signal that we are going to have it. Modulate, you change the one that we are going to have it. So we want to see what is meant by modulation that we are going to have. Now from frequency translation, we are coming into modulation, right? A frequency translation, nothing but a modulation. That's what we are having. But what exactly we mean by a modulation? So you have a signal AC cos omega ct plus phi t. So what are the parameters in this signal? What are the parameters in this signal? AC, the amplitude, omega c, the frequency, and phi, the phase. Three parameters are there in your carrier signal: the amplitude, frequency, and phase. Right, so this we may be writing as AC cos theta t also, where theta we call it the angle of the signal that we are going to have it. So combined we may say that this is angle variation, amplitude and angle variation or angle modulation that we are going to have it. And specifically in the angle we are having both frequency and phase variations or the phase modulation that we are going to have it. So we say that you have your amplitude modulation, frequency modulation, and phase modulation that we are going to have. Three parameters are there in your sinusoidal signal. So how we are going to change your parameters, amplitude or phase or frequency that we are going to have it. So this we are going to have it, change this amplitude or frequency or the phase in accordance with the instantaneous amplitude of our baseband signal or the modulating signal. So when you say that amplitude modulation AM, as the baseband signal varies, whatever the variation that you are going to, that represents variation in your carrier variations also. So we can state the amplitude modulation as the instantaneous, the modulation of the variation of the amplitude of the carrier in accordance with the instantaneous amplitude of the baseband signal, that we call it as amplitude modulation. Whereas instead of amplitude, if you substitute frequency, that will be a frequency modulation that we are going to have it. So what is the statement for frequency modulation? Variation of the frequency of the carrier in accordance with the instantaneous amplitude of your baseband signal that we are going to have. Similarly, phase also. So you have amplitude modulation, frequency modulation, and phase modulation that we are going to have it. As you look into this, this is what your signal that we are having, and as the signal changes, your carrier is a fixed amplitude that we are going to have AC cos omega ct. That is changing the amplitude. When it is increasing, the amplitude is increasing. When the amplitude is going negative, the amplitude of carrier is decreasing, and then again increasing as the input signal is going to be increasing. So your amplitude of your AM signal is going to be increasing or decreasing depending on the amplitude of your baseband signal. Similar the frequency also. When the amplitude is highest, we are having highest frequency, and when they are having a negative signal, you have the lowest frequency that we are going to have it. So like this, we have the both amplitude variation or the frequency variation or the angle variation that we are going to have it. So this is what your variation of the carrier amplitude or carrier frequency. In the case of amplitude modulation, amplitude is changing, whereas in the case of frequency modulation, amplitude is not changing. You have a fixed amplitude, right? Only frequency is changing. So at the receiving end, in the channel, if you have any addition of the noise that we are going to have it, amplitude variations cannot be reduced in the amplitude modulation by reducing the amplitude variations, by reducing noise. Whereas in the case of FM, You can eliminate that because your amplitude is always constant. The modulation is there only in the frequency. Therefore, you limit this to a constant amplitude, then go for detection to find the frequency variation that we are going to have. Therefore, as far as noise performance is concerned, FM is going to be better than the AM signal that we are going to have. So that because any variation in the amplitude of the AM signal may be your variations of your baseband signal itself. You can't eliminate there. Whereas in the FM, you can eliminate these amplitude variations and find out only the frequency variations that we are going to have. So that is about your amplitude modulation and frequency modulation with that of your three parameters that we are going to have of your baseband signal: amplitude, frequency, and phase that we are going to have it. Now we'll see what is amplitude modulation. We'll go further into details because the first unit is going to be talking about this frequency translation and then about your amplitude modulation. The next unit we will see further variations that we are going to have it. So your amplitude modulation so what is that amplitude modulation that we are going to have it? You have your Vm of t as Am cos omega m of t. This is what your baseband signal. And what is the carrier signal? For the time being, let us say that your phase is 0. Okay? Phi of t is 0 for our convenience. We say that this is only AC cos omega Ct that we are going to have it. What is amplitude modulation? The amplitude of this carrier has to change in accordance with your baseband signal, Vm of t or m of t. So this I will say that some m of t. This is not Am cos omega mt, but general m of t that we are going to have a voice signal. Therefore, your Vam of t one plus Ka m of t into cos omega Ct. You have the amplitude modulated signal Vam of t as AC into 1 plus Ka m of t cos omega Ct. Suppose m of t is 0. What is the output? M of t is 0. It is only carrier, no modulation. Right? That means you don't have any amplitude for your baseband signal. M of t is 0. No modulation. That means carrier has to come without any change. That's what we are going to have it. And this Ka, we introduce this, we have what you call amplitude sensitivity of your modulator. Ka is the amplitude sensitivity of the modulator. So if you have this Ka m of t is less than 1, suppose m of t is positive, right? K m of t is less than or equal to 1, less than 1. Then what will happen? If you say that K m t is equal to 1, let us say positive. This is 1 plus 1, 2. 2 AC cos omega Ct. That is, the amplitude is now double. Whereas, suppose m of t is negative and k m of t is minus 1. Then what will happen? 1 to 1, 0. So when you have this negative peak of the sinusoidal signal, that what you have seen previously, when you have positive peak, this is 1 plus 1. When you have negative peak, you are having 1 minus 1. That means that is going to give you 0. But what we are saying is kmt is not equal to 1 but less than 1. So it will never go to 0 and never go to the maximum twice the value. So in between these two values, less than twice AC or 0. It will be varying between these two values, your amplitude of your carrier signal. Frequency is the same, cos omega ct. You are going to get the required modification that we are going to have it. So we are getting the amplitude modulated signal with the instantaneous amplitude of your baseband signal. As m of t changes, the 1 plus kmt is going to change the amplitude, increasing or decreasing, depending on m of t is positive or negative. So your amplitude is increasing or decreasing. That's what your amplitude modulation. Amplitude is increasing or decreasing, depending on the input signal that we are going to have it. If input is positive and going to maximum, it is going to have a maximum amplitude. When input is negative and is coming to the minimum, then it is going to be the minimum output signal that we are going to have it. So amplitude of your carrier has changed to minimum to maximum signal that we are going to have it. So depending on instantaneous amplitude of your baseband signal, your output modulated signal is going to change its amplitude, keeping the carrier the same. Carrier frequency has not changed at any place that we are going to have it. So it is only the cos omega ct that we are going to have it. But where is the baseband signal frequency coming into picture? So that we'll see when we have the spectral lines that we are going to have it. Let us say that this is your m of f. Zero to fm, right? That we are having 1 plus km of t into cos omega ct. Or if you expand this, what will happen? AC cos omega ct. Because this is 1, this will be equal to AC cos omega ct plus AC Ka m of t into cos omega ct. What is that AC cos omega ct gives you? The carrier signal. So what is the spectrum of that? So you have Fc and you have minus Fc. Two spikes, impulses at Fc and minus Fc. That is for the first part, 1. And AC Ka mt cos omega ct. So mt cos omega ct. So m of f plus Fc, m of f minus Fc with the amplitude AC Ka by 2 that we are going to have it. Therefore, you are going to have the spectrum like this. So in the frequency translation, we didn't have these spikes because they are only mt into cos omega ct. But whereas now you have this 1 also. Previously we don't have this 1. In the frequency translation, what we have discussed previously is only Vc of t into Vm of t. Okay, now we have this 1 also. Because of that, we have these 2 frequency components at the carrier frequency also, f of c and minus f of c that we are going to have it. So here this is f of c plus f of m, and this is f of c minus f of m. Similarly here this is minus fc plus fm, and this is minus FC minus FM. So FC and FC plus FM. FC and FC plus FM. The frequency component that we are going to have it is changed from FC to FC plus FM. So this we call it as the upper side band. FC and FC plus FM. This range we call it as the upper side band. And negative of this FC minus FM. This we call it as the lower side band. Upper side band and lower side band. FC to FC plus FM we are saying upper side band. What is the minus of that? Minus FC minus FC minus FM. That is this part. Minus FC minus FC minus FM. So this will be our upper side band. Let's say this. So this will be the upper side band of the negative frequency. And this is our lower side band. FC minus FM and FC. So minus FC minus FC plus FM. Whatever lower side band. What is the half here? Half omega MC. Omega M. Omega plus omega M is upper side band. That's divided. Omega M is the lower side. What we are having? FC minus FM. That's minus omega M. The lower side band. That's plus omega M is the upper side band of the omega. Therefore, in this signal, we have the carrier. Half omega C to the upper side band and lower side band. Components that we are going to have. Suppose here, instead of M of T, I'll say that this is M cos omega MT. Therefore, this we can write it as AC cos omega CT. Plus M AC by 2 cos omega M of T plus by 2 cos omega T minus M of T. Carrier upper side band and lower side band. The components of the other side. Whatever M this M is called as the modulation index. The modulation index. Right? M is the modulation index. How to calculate this modulation index that we are going to have it? When cos omega mt is the maximum, what is the maximum value of cos omega mt? 1. When that is going to be there, this is going to be AC into 1 plus m. Okay? Having a maximum amplitude of your cos omega ct. Therefore, maximum, this I represent as A max, maximum of the modulated signal, VAM max, as AC into 1 plus m. Then A minimum will be equal to AC into 1 minus m, because when this is minus 1 to 1 minus m, A maximum is AC into 1 plus m, A minimum is AC into 1 minus m. Therefore, what will be m value in terms of this maximum and minimum? So we can say that this is the maximum amplitude and this is the minimum amplitude. A max and A minimum, that we are going to have it. So A max and A minimum is AC into 1 plus m and AC into 1 minus m. Actually, that is peak to peak is going to be 2A maximum, and here minimum value is 2A minimum. Okay. So what will be the m value in terms of A max and A minimum? A max minus A min by 2AC, or A max plus A min. 2AC is nothing but A max plus A min. We add these two, this will become 2AC. Therefore, if you know the maximum amplitude and minimum amplitude of your base, the modulated signal, you can calculate the modulation index. Or if you multiply this with 100, this we call it as the percentage modulation. If you multiply this m with 100, then we call it as the percentage modulation that we are going to have it. So how much percentage of modulation we are going to have it depends on this modulation index that we are going to have it. Right? So we have discussed about the general communication system and what is the need for communication, the modulation that we are going to have it, or what are the advantages of frequency translation. Sometimes we will be calling as need for modulation, or you will put the question as advantages of frequency translation. Both are the same. The 4 points that we have seen: the frequency multiplexing, effective radiation, narrow banding, and common processing. Then we have seen the frequency translation, how we are going to have a linear modulation that we are going to have it. Your frequency translation is going to be linear depending on number of baseband components. Your output components are fixed twice that of the value that we are going to have it. Then we have seen what is amplitude modulation, frequency modulation, and phase modulation, and what are the definitions of this, how the waveforms are going to be looking like. Then we have seen the amplitude modulation and the percentage modulation index that we are going to have. Modulation index or the percentage modulation that we are going to have. So any doubts? Any queries? No queries? Anyway, they may be having queries. So let them put to their mentor, and then we'll have the answers in the subsequent classes. Okay, thank you.